Well, let's go ahead and get started. And I should have had this loaded before I started the video, but bear with me just a few seconds. Now we're looking at inverse functions to begin with. And the first topic is to identify one-to-one functions. Well, let's first talk a little bit about one-to-one functions. For a one-to-one function, it says for every x there is only one y, and for every y there is only one x. So it goes both ways. Now that's a little bit hard definition to work with. We got an easier definition of a one-to-one function. It says if you have any of the following, it is not a one-to-one function. If you have even powers, if you have the absolute value, if you have the plus or minus symbol, or if you got x is equal to a number, or y is equal to a number. And that's all you have, like x equals 3 and y is equal to 5. Unless there is a condition put on x. An example of that. Y is equal to x squared. Normally on that, since it has an even power, it would not be a one-to-one function. But if we put a condition where we're saying x is greater than 0, by putting that condition on there, we're making sure that it is a one-to-one function. There's other reasons why you might put a condition on there, but that's the reason why we put a condition in this section. We also got a horizontal line test. We had the vertical line test that says if any vertical line intersects your graph at two or more places, it's not a function. Well, we got the horizontal line test. It says if any horizontal line intersects the graph at two or more places, then it is not one-to-one. An example of this. Here's a graph of y is equal to x squared. We know the fact that it has an even power, that it's not a one-to-one function. But if I draw a horizontal line here, you see it intersects at two or more places. So this is not a one-to-one function. So that's what I mean by the horizontal line test. Now the reason why we care about that is if it is a one-to-one function, then it has an inverse. Otherwise, it does not have an inverse. So for like this one right here, this one was asking us about the existence of an inverse function. We would say there's no inverse function. Now the second item here says determine whether two functions are inverse. And let me make up an example here. First, let's take a look at the graphical definition of an inverse. Then we'll take a look at the algebraic. We got a point here, -4, -4, 1. And we got a point here that's -1, 0. And we got a point here that's 1, 2. Now if I connect them together, this would be our function, let's say. Now we have a line goes right through the middle here. This is a line y is equal to x. Now inverses are symmetric to the line y is equal to x. Which means, I don't draw these very well, so you have to use your imagination. This point is -4, 1, so our inverse would have 1, -4. This point here is -1, 0, so our inverse would have 0, -1. And this point here is 1, 2, so our inverse would have 2, 1. And then after I draw that, I can draw my line through it. And this would be our inverse. And you see I got these wider apart. They're supposed to be symmetric though, which means if I take this part of the graph here and flip it, reflect it across the line y is equal to x, it should land exactly on this part of the graph. And if I had drawn it a little bit better, you would see that. But that's our graphical definition. And let me clear that off. And let's take a look at the algebraic definition. F, or I should say of an inverse of a function. F and G are functions. F and G are inverses of each other if the following is true. Now I'll put this in there and I'll make it a little bigger after I get it inserted. If the composition of F and G is equal to X, and the composition of G and F is equal to X. There we go. So we need to find the composition to determine if two functions are inverses of each other, algebraically. Let's take a look at an example. Say we got f of x is equal to 3x minus 1, and g of x is equal to x plus 1 over 3. And the question is, are they inverses of each other? Well, I had to find a composition going both ways. So composition of f and g is f of g. Now we're going to go to our f of x, which is 3x minus 1, and where our x was, we put in parentheses. Now, evaluating a function is always the same. Whatever's inside this parentheses is what you put in here. So we'll put g in there. But g was equal to x plus 1 over 3. Now here the 3's would cancel. We got x plus 1 minus 1. And 1 minus 1 would cancel and gives us x. And that's our first piece. Now it has to go both ways though. Composition g and f is g of f. So we're going to take our g of x, which is x plus 1 over 3, and where our x was, we put in parentheses. And evaluating the function is always the same. Whatever's inside this parentheses is automatically what you put here, so we put f there. But f is equal to 3x minus 1. So the negative 1 plus 1 cancels. We got 3x over 3. 3's would cancel and gives us x. Now since both of them give us x, the answer to the question, are these inverses of each other? The answer would be yes. Now, if one of them gives you something besides x, gives you x plus 3, for example, or gives you 7, but gives you anything except for x, then the answer would be no. They're not inverses of each other. Okay, let's take a look at the next topic. Let me clear this off. And this one is to find the inverse. So finding the inverse of a function. Note, f of x must be 1 to 1. Of course, it's assumed as a function because we're finding the inverse of a function, but it also must be 1 to 1. Our first step is to replace f of x with y. Step 2 is to interchange x and y, swap them. Step 3 is to solve for y. And step 4 is to replace y with our inverse notation, what looks like f to the negative 1 power. It's not negative 1 power, but that's what the inverse notation looks like. And step 5, if necessary, use the graph to figure out how to make the inverse 1 to 1. Okay, so if I had y is equal to 7x plus 2. Step 1. Replace our f of x with y. I should have had notation there, shouldn't I? Let's try again. F of x is equal to 7x plus 2. I didn't want the first step to already be done. Okay, step 1. Replace f of x with y. So we got y is equal to 7x plus 2. There's nothing wrong with the problem starting out at this point, but I wanted to show all the steps, or at least the first 4. Step 2, interchange x and y. Swap them. So where the y is, you put an x, and where the x is, you put a y. And then step 3 is to solve for y. In this case, I'll take the 2 over, and then I'll divide both sides by 7. Divide those by 7, those 7's cancel. And we got y is equal to x minus 2 over 7. Now step 4 is to put our inverse notation in. So the inverse of f is equal to x minus 2 over 7. And that would be our answer. We don't have to do step 5. There's no even powers. There's no absolute value. There's no plus or minus symbol. No x equals or y equals a number. Let's take a look at the cube root of x plus 5. And we want to find the inverse. Well, step 1, replace f of x with y. So we got y is equal to the cube root of x plus 5. Step 2, interchange x and y, swap them. Where the y is, you put an x, and where the x is, you put a y. Step 3 is to solve for y. Well, the cube root I can rewrite as y plus 5th to the, or y plus 5 to the 1/3 power. And we can get rid of the exponent here by raising both sides to a power equal to reciprocal. Reciprocal means fraction flipped. So take both sides to the 3/1 power. Now normally we have to ask the question, do we need to put a plus or minus on the other side? But since this is an odd number on top, so odd number on top means no plus or minus symbol. So that's x to the 3rd equals, this one and this one cancels, the 3's cancel, and that leaves us y plus 5. And I'll take the 5 over. And we get y is equal to x to the 5th, or y is equal to x to the 3rd minus 5. And then step 4, we'll put our notation in. So the inverse of f is equal to x to the 3rd minus 5. And that's our answer. Let me clear that off. And we'll move on to section 4.2, exponential functions. And I'm going to grab a quick drink. First thing we'll do is we'll graph exponential functions. Let's say, for example, we want to graph y is equal to 3 to the x minus 2 power. The trick to it is, if you got more than a single number, single variable, single anything in your exponent, when you put in your calculator, you have to put parentheses around like this. Other than that, you just enter as you see it. And let me reset my calculator and everything. There we go. Okay. So, to graph this, we're going to go to y equals. You press clear to clear out wherever's in that line. And then we're going to have 3 to the x minus 2 power. So we'll do 3 and then caret, beginning parentheses, x minus 2, closing parentheses, and then graph. Some of the newer T84s have an exponent mode where when you do the caret, it puts it up an exponent. You don't need the parentheses at that point, but they don't hurt anything either. So our graph would look like this right here. Now, depending upon the homework system, some require you to have a little bit more precise graphs and just generally what it looks like. If you need precise points, you can go to the table. But first I do table setup. If you do second window, you want independent to say ask. If it doesn't say ask, you down arrow, and then right arrow to ask, and then you press enter one time. And that'll change the highlighting to ask. Now if you do second graph to go in your table, you can plug in values. So I could try 0, 1, 2, 3, 4, 5, and so on. Now, I would steer away from these decimals unless the system allowed you to do that, you want to go with the integers here: 2, 1, 3, 3, 4, 9. Those are a lot easier to actually sketch on if you have to draw it yourself. Now evaluate the exponential function base e. Okay. So let me clear this off. If you got e to the 3.1 power, for example. Now e is a number. It's kind of like pi. It's 2.7, a bunch of decimal places. To get to e on your calculator, we're going to exit out, do second mode. Then to get to e, you do second, and then you push your ln button. This is your natural log button. It'll put the e, it'll put the caret, put the beginning parentheses. Then we got 3.1, and press enter. And then you round however many decimal places. So 22.1980, 198, and that'll be your answer. Now here it's asking us to use the exponential functions to compute compound interest. So let's talk about our compound interest formulas. You got two types of formulas. One of them does not say continuous. And that'd be a is equal to p times 1 plus r over n to the nt power The other type does say continuous. It'll say compounded continuously. That's a is equal to pe to the rt power. Now a would be your ending amount. P is your beginning amount or your principal. R is your rate, and this would be in decimal form. 3% would be 0.03. T is your time, and this is in years. And then N is the number of times compounded per year. Now, compounded is a fancy business term. It means calculated. But it's a little bit more than that. They calculate the interest, compute it, and then they take that interest and we put it back into the account. So it compounds, it builds. So let's say that we have $1,000 we put into the bank. We're going to do it at 2% interest. We're going to leave it in there for 10 years. And it's compounded monthly. So it doesn't say anything about continuous. Well, when it says compounded monthly, that tells us what n is going to be, because n is the number of times compounded per year. So if it says monthly, then n would be 12. So we got a is equal to p times 1 plus r over n to the nt power. So we got 1,000, 1 plus r, which is 0.02, divided by n, which is 12, raised to the nt power, which would be 12 times t, which is 10. Now put a little x there to indicate multiplication. It's always best to do a little bit of calculation before you plug it in your calculator. What I mean by a little bit of calculation is this 12 times 10. If you can do that in your head, 120, then that saves you some extra effort on your calculator. Okay, so if I come over here, I do 1,000, beginning parentheses, 1 plus 0.02 divided by 12, closing parentheses, caret 120. And we get 1,221.20 to 2 decimal places. So if we invest $1,000 in, leave it for 10 years at 2%, compounded monthly, this is how much we'll have at the end of those 10 years. Let's say I got 1,000 at 5%. We're going to leave it in there for 20 years. And it's compounded continuously. Well, since this says the word continuous, we use the PERT formula. So we plug in what we're given. P is 1,000. E to the R is 0.05, times T, which is 20. And I put a little X there for multiplication. Now, I'm not very good at decimals, so I'm not going to try to do 0.05 times 20 in my head. Probably could, but I might screw it up. Doesn't matter so much on this one. If I put 1,000 E, and that's second natural log, second ln, and then 0.05 times 20. The trick to plugging this one in your calculator is do not put any extra parentheses in there. So you plug it in with as few parentheses as possible. None if you can do it. You notice I didn't type a one beginning parentheses. It put that beginning parentheses on there for us. And then press enter. So we got 2,718.28. So if you have $1,000, you put in the account at 5% for 20 years, compounding continuously, you'll have a little bit over $2,700 at the end of that time. Okay, let me clear that off. Applications oftentimes involves word problems around the interest. Now, log function, section 4.3. First thing talks about convert between log and exponential forms. So let's talk about that. We have our log form, which is log base b of q is equal to p. And then we have our corresponding exponential form, that's b to the p power is equal to q. So if I have a problem, it's log base 3 of x minus 2 is equal to 5. And this is log form, and we want to rewrite it in exponential form. Well, we have to identify our different letters here. B is our base, and it's whatever number follows your log that's a little bit smaller, it's set down. So that's our B. And then what follows that is your Q. So the x minus 2 is our Q. And then the other side of the equals is our P. So the 5 is our P. And our exponential form is b to the p is equal q. So we just plug in what we identified. B was 3, p is 5, and q is x minus 2. And that would be our answer. Now we have two special cases. One of them is where instead of a log, you have ln. Like natural log of 6 is equal to 6. Natural log of x is equal to 6. If you have ln, then there is no number here, there's no base. Our base by default for ln is e. So natural log has base e. And then what follows that is your q. So q is equal to x. And what's on the other side is your p. So p is equal to 6. So our exponential form is b to the p is equal to q. So we plug in what we identified. B was e, p was 6, and q was x. And that's our answer. There's one more special case. Let's say that I have, let me pick my pop up, I just dropped it. Luckily the lid was still on it. Let's say I have log 7 is equal to x. There is no base. It says log, but there's no base. If it says log and there's no base, this is base 10. This is our common log. And then again, whatever follows that is your q, and the other side is your p. So our exponential form is b to the p is equal to q. So we plug in what we identified. We said b was 10, p is x, and q is 7. And that'd be our answer. Now that's going from log form to exponential form. So let's go the other direction. Let me clear these off. And let's say I have 2 to the third power is equal to x. It's an exponential form. Well, same idea. We have to identify our b, p, and q. Now p is your power. So whatever your power is, your exponent here, that's your p. And then what's to the left of it is your b, your base. And then the other side of the equals is your q. Now our log form is log base b of q is equal to p. So we plug in what we identified. So we got log base b, which is 2, of q, which we said was x, is equal to p, which is 3. And that would be our answer. Now sometimes the trick is rewriting it into the correct form. For example, if I had this, the cube root of 5 is equal to x. Throughout this entire chapter, you very rarely want any radicals at all. If you see a radical, you want to rewrite it. Well, I can rewrite this as 5 to the 1/3 power. Remember how that works. Whatever power's in here, and if there isn't one, you put 1 there by default. Whatever that is goes up on top. And then whatever your base is, or I mean whatever your index is, sorry. In this case, it's 3 is what goes down below. So we're going to have 5 to the 1/3 is equal to x. And now this is in our exponential form. Our power, our exponent, which is 1/3, will be p. The number immediately to the left of it will be our b, and the other side of the equals will be our q. So our log form says we got log base b of q is equal to p. So we plug in what we identified. B was 5, q was x, and p is 1/3. And that'd be our answer. Now evaluating log expressions. Let's talk about that. There's some of them that you can do by hand, as in this example. I'm going to work this problem, and then I'm going to write the property down, the formula. Formula make it look complex. It's a fairly simple idea. Sometimes it's not so simple to get in the correct form. That's the challenging part. Now notice here our base is 2. What we try to do is we try to rewrite the number following that as 2 to the power. Well, 8 would be 2 to the 3rd. Now if you can get these two numbers to match here, then the log of those two numbers is going to cancel away. So log and those 2's cancel away. And our 3 drops out of the exponent, and that's our answer. Now I said it's a fairly simple idea, but not always easy to get in the right form. Let's say I had this. And we're going to try to rewrite it. Our base is 3, which means we have to rewrite it as 3 to a power. Well, first off, I can rewrite the 5th root of 27 as 27 to the 1/5 power. Remember, we never want radicals. And, well, I still don't got it as 3 to a power, but I know 27 is 3 to the 3rd. So I can rewrite that as 3 to the 3rd. Now, when you're raising one exponent to another exponent, you multiply them together. 3 times 1/5. So we're going to have 3 to the 3/5 power. And now it's almost in the right form. I just need to take this and put it up on top. Well, you got a property says you can move something opposite of where it's at in a fraction, and the sign of the exponent changes. So this becomes 3 to the negative 3/5 power. Now again, if these two numbers match, then the log in those two numbers is going to cancel, and our answer would be negative 3/5. Now the property that I promised you says you got log base b of b to the p power. That's going to equal to p. So that's what the property says. Now there's another way to evaluate a log. Let me grab a drink here, assuming it's not still shook up. Excuse me. Some problems you can plug directly in the calculator. Let's say you have natural log of 3. We have an ln button. So to plug this in, you just simply push your ln and then 3. And that gives you your answer. 1.099. Take it 3 decimal places. You would take it to however many your problem indicates. Let's say I had log of 5. We have a log 5, or we have a log button. Log is base 10, and I put 5 in, and then press enter. And that gives us 0.699. So no problem there. The problem is where you actually have a base, like you have 3 there. We don't have a base 3 button. We have an ln button, which is base E. We have a log button, which is base 10. We don't have base 3. We have to rewrite this using the change of base. The change of base says we're going to rewrite this as log 8 over log 3. Now how the change of base works is whatever follows your log always goes up on top. Whatever your base is always goes down below. Change of base says you can actually rewrite it as any base, but log is good as any because you have a log button. So to put this in your calculator then, if I do log 8 close parentheses divided by log 3 and then press enter, we get 1.893. And that's how you would evaluate log expressions on your calculator. Now we have our basic properties of logs, so let's talk about those. Let me clear this off. We got 3 big ones. There's minor properties, but there's 3 big properties. We got log of something plus log of something. Addition becomes multiplication. If you have log of something minus log of something, subtraction becomes division. If you have a number in front of your log, then you can take that number and put it as your power. Now, strictly speaking, it does not have to be a number. You can even have a variable out in front of your log. Typically, you see numbers. Variables have an extra problem where you have to consider some answers that aren't possible. In some cases, you'll start off plus 1. You'll start off with a single log. And these apply no matter what your these properties apply no matter what your base is. This is base 10. Now, first off, we know we don't like radicals. So the square root of x plus 1 we rewrite as x plus 1 to the 1/2. Always your question is the same on this. You ask yourself, what's the main thing that's happening? And when I say main thing, I'm talking about what would encompass everything following the log. Like, for example, the 1/2 power. Would that be the main thing? No, because the x squared wouldn't be affected. The 1/2 only affects the x plus 1. The x squared would not be the main thing. The main thing that would be happening is we got this times this, multiplication. That would use everything following the log. Well, from our property, multiplication we can rewrite going the other direction as addition. So this becomes log x squared plus log x plus 1 to the 1/2. Now you're still asking yourself the main thing that's happening. There's only one thing left here is second power. And our third property says if you got a power, an exponent, you can put it out in front of your log. So that's going to become 2 log x. Over here, there's one thing left, the 1/2 power. So you put it out in front of your log. And you got 1/2 log x plus 1. Now that's as much as we can do. You might say, well, how about this x plus 1? Can you break that down any? No, we don't have any property that helps us with addition. Our addition property is a little bit different. It says if you got log of something plus log of something, it means you have a log on each separate piece. It does not say log of x plus 1. Okay, let me look at another example. Log of the cube root of x squared over y z to the 5th. First off, we don't want radicals, so I'll rewrite that. X squared y z to the 5th, rewrite it to the 1/3 power. That's what the cube root becomes. Now the main thing that's happening here, we got second power, we got the 5th power, we got division, we got multiplication on the bottom here, and we got this power out here. The main thing that's happening is the power, the 1/3 power. The 1/3 is what would be affecting everything, because everything's being raised to 1/3 power. Well, from our third property, it says if you have a power, you can put it on front of the log. So we got 1/3 log x squared over y z to the 5th. Now, as I rewrite these logs from here on out, that 1/3 has to be in front of every log. Now we got second power, we got the 5th power, we got multiplication, we got division. The main thing that's happening if we use everything is division, because we got all of this divided by all of this. Well, division from property 2 becomes subtraction. So we're going to have 1/3 log x squared minus 1/3 log yz to the 5th. Now in our first log here, there's only one thing left, the power. So we take the power and put it out in front. Now when you put it out in front, you multiply it by what's already there. So we got 1/3 times 2 log x minus, and I'm going to put a bracket here because as I rewrite this, actually I need to put the 1/3 first. So I'll put a bracket here. As I rewrite this negative 1/3 that's out in front has to affect everything that follows it. Okay, so we got, the main thing happening here is not the fifth power, that's only affecting the z, but we got multiplication, y times z to the fifth. That becomes addition, so I got log y plus log z to the fifth. Now I'm going to go ahead and take that negative 1/3 through. This is 2/3 log x minus 1/3 log y minus 1/3 log z to the fifth. I always show a lot more steps than you need to on homework. Now there's nothing left to do here, nothing left to do here. Only thing left here is the fifth power. We can take that and put it out in front. So that gives us 2/3 log x minus 1/3 log y minus 5/3 log z. And that would be our answer. Okay, now let's take a look at some problems or a problem going the other direction. Let's say I had log x minus 7 log y. So they're separate logs. And one go the other direction. Well, the only time you can use these first two properties going the other direction is you got log of something plus log of something and log of something minus log of something. You cannot have any numbers in front of your logs. So before you can apply properties 1 and 2, you have to apply property 3, get rid of any numbers in front of the logs. So here, I'll take this 7 and put it as my power. So I'm going to have log x minus log y to the 7th. Now I have log of something minus log of something. Subtraction becomes division. So we're going to have log of x over y to the 7th. And our goal is to get a single log. Let's say I got 3 log x minus 4 log y plus 1/2 log z. Well, same thing. We can't use properties 1 and 2 while there's numbers in front of our logs. So property 3, we'll take those numbers, put them as our power. So I got log x to the 3rd minus log y to the 4th plus log z to the 1/2. Now, we handle these from left to right, so I'll do this one first. We got log of something minus log of something. Well, subtraction becomes division. So we got log x to the 3rd over y to the 4th plus log z to the 1/2. Now addition becomes multiplication, so we're going to have log of x to the 3rd, y to the 4th, times z to the 1/2. Now I'm going to put that z to the 1/2 up on top, but I'm going to rewrite it back in the radical form, and that'd be the square root of z. And this would be our answer. Now to graph log functions, really not too much exciting here, but I do want to talk about it. Actually, I guess I should have read ahead. Product quotient power property is what I just showed you up here with the basic properties. I guess I wanted them down here. So I've already done, actually, all of section 4.4. Okay. First off, if you want to graph something that does not have any extra base, like log x minus 1 or natural log, ln, you do nothing but simply type it in. So if I come here, go to y equals, press clear, then I just put in my log x minus 1, and then you press graph. Now, what I need to point out here is it looks like it just stops. These graphs never just stop. It keeps going down forever. It's a flaw with the calculator. So what your graph should look like is this right here. So that would be our graph. Remember we looked at the change of base earlier. Now if you have y is equal to log base 3 of x minus 1. So instead of our standard x minus 1, we have now a different base. You're going to use a change of base on this. So we're going to rewrite that as log of x minus 1 over log of 3. Now remember how the change of base works. Whatever follows your log is what goes up on top, and whatever your base is what goes down here. Now, the benefit of that is once you got it rewritten, you can plug it straight in your calculator. So if I go to y equals, clear, and do log x minus 1, close parentheses, divided by log 3, and then graph, this would be our answer. But again, they never just stop. This keeps going down forever like that. That'd be our graph. And like I said, we've looked at all these product, quotient, power properties. I didn't mention that they have names, but this is the product property, quotient property, and power property. We wrote a log expression in expanded form. That's where you start with a single log and you expand it in separate logs. And we took separate logs, we merged it into a single log. And we've also applied change of base. So let's get down here and want to solve a exponential equation. I'll grab a drink while I'm here too. We have a property called the equality of exponents. And equality of exponents says if you got b to the p power is equal to b to the q power. The b represents a number, and they're the same, like 2 to the power equals 2 to the power. Then you set the exponents equal to each other. So you'd have p is equal to q. Very simple idea. Sometimes not so simple to get in the right form, though. Let's say I got 2 to the x plus 3 is equal to 8. Well, we start with our larger number. So start with the 8. And we're going to try to rewrite it as 2 to the power. Well, 8 is 2 to the third. Equality of exponents says if you can rewrite each of these as 2 to the power, then the 2 is going to cancel. And you set the exponents equal to each other. So we got x plus 3 is equal to 3. And then you solve for x. So take 3 over. And we get x equal to 0. Let's say I have 4 to the x is equal to 8 to the x minus 1. Okay. Now if we start with a large number, start with 8. We cannot rewrite it as 4 to the power. But now in this example, I look at both sides, and I can rewrite both sides as 2 to the power. This would be 2 to the second power. This one would be 2 to the third power. Now notice when I put the new exponent up, you multiply times the exponent that's already there. So 2 times x and 3 times x minus 1. Since there's 2 or more terms here, I had to put parentheses around it. The equality of exponents says if you rewrite both of them as 2 to the power, you can cancel the 2's. And set the exponents equal to each other. And then I want to solve this. 3 times x is 3x. 3 times negative 1 is negative 3. Get everything with an x on one side, numbers on the other. So take negative 3 to the left side. Now take 2x to the right side. And 3x minus 2x gives us x equals 3. And that's our answer. Now that's the equality of exponents. But obviously that doesn't work all the time. For example, if I have 3 to the x is equal to 5, there is no way you're going to be able to rewrite 5 as 3 to a power. So we have a method for solving an exponential equation. Step 1. Get the part with the variable and the exponent by itself on one side of the equals. Nothing in front of it, nothing after it. Step 2. Take natural log of both sides. Step 3. Use properties of logs to get the variable out of the exponent. And step 4, solve for x, whatever that means. Might be a linear equation, might be a quadratic equation at that point. Step 1, get the part of the variable and the exponent by itself on one side. Well, it's by itself. There's nothing in front of the 3, there's nothing after. You just got 3 to the power. Step 2, take natural log of both sides. So we got natural log of 3 to the x is equal to natural log of 5. Step 3, use properties logs, get the variable out of the exponent. If we have log of something to a power, you can take the power and put it out in front. So it becomes x natural log of 3 is equal to natural log of 5. Now step 4 is solve for x. This is a linear equation. Natural log of 3 is just a number. So to get the x by itself, we'll divide both sides by that number. Those natural log of 3's cancel. You might be tempted to cancel the LN's, but you can't. This would be our exact answer, and we could plug it in our calculator with a natural log button if we wanted to see what the approximation was. Let's say I had e to the x minus 1 is equal to 7. Step 1. Get the part of the variable and the exponent by itself on one side. Well, this is the part of the variable and the exponent. It's got a minus 1 after it. So you can always do the opposite operation to get rid of whatever's there. So this is a subtraction, minus 1, so I can add 1 to both sides. Negative 1 plus 1 cancels. 7 plus 1 is 8. And then step 2. Take natural log of both sides. So we'll have natural log of e to the x is equal to natural log of 8. Now over here, remember natural log has a base of e. Excuse me. And since those e's match, the ln and the e is going to cancel. This is step 3. And the exponent drops down out of the exponent. And actually at that point, we've got it solved. That always happens. Natural log and e will always cancel each other away. Now let's say and this gets into down here. We're talking about modeling and so forth and some of these. Let's say I had a problem where they told us the ending amount is $2,000 and the principal was 1,200, and they tell us the rate was 2%, and it's compounded continuously, and they want to know how long did we leave it in the account. So this is an application problem dealing with this concept. Now remember, if it's compounded continuously, it's this formula here, the PERT formula. So I'll plug in my values. 2,000, P is 1,200, E to the R, which is 0.02, T power. Now we want to solve for T, and this is an exponential equation. An exponential equation means you got a variable and the exponent. So our first step is to get the part of the variable and the exponent by itself on one side. Well, there's 1,200 in front of it, so I'll divide both sides by 1,200. There we go. Now you can simplify that if you want, but there's really not much need for that. So step 2, take natural log of both sides. So we got natural log 2,000 over 1,200 equals natural log of E to the 0.02 T. Now remember, natural log and E are going to cancel each other, so that gives you a 0.02 T. And then we're going to divide both sides by 0.02. When I said there's not a whole lot of need to simplify that, because you're going to end up plugging in your calculator anyway. So if you want to simplify it, that's fine. But you know, if you're going to have to use a calculator, there's not much need. I'll do second mode, natural log 2,000 divided by 1,200, close parentheses, divided by 0.02. And T would equal 25.54 to 2 decimal places. So that's how you can use our exponential equations step-by-step approach to solve a compound interest problem for one of the variables up in the exponent. Now let me clear this off. And next problem we'll take a look at is a log equation. What this would look like is log base 2 of x minus 1 is equal to 3. So it's an equation with a log. So we got solving log equations. Step 1. Get everything with a log on one side, numbers, constant terms on the other side. Step 2, use properties of logs or basic algebra to get a single log on that side. Step 3, use the definition of a log to rewrite in exponent form. Step 4 is solve for x. And then step 5 is to check your answers. You don't have to fully check it, just to make sure you don't got a log of 0 or log of negative number. Step 1. Get everything with a log on one side, numbers on the other side. That's done. Step 2. Get a single log. That's done. Step 3. Use definition log to rewrite in exponent form. Remember our B, and P, and Q? Now whatever your number that follows your log, the smaller, that's your base. That's your B. And then what follows that is your Q, and then the other side of the equals is your P. Now our exponential form is b to the p is equal to q. So we plug in what we identified. B is 2, p is 3, and q is x minus 1. And then step 4 is we want to solve for x. 2 to the third is 8. Take negative 1 over. We got 8 plus 1 is equal to x. Or we get x is equal to 9. Maybe. Remember, we have to semi-check it to make sure we don't got log of 0 or log of negative number. If I put the 9 back up in my original problem, 9 minus 1 is 8. And that's fine. It's not negative, it's not 0. Now I'm going to do the first steps on these next two examples, but I won't finish them because I can't make these up off the fly and have them actually work out. But let's say I have this right here. Now our first step says get everything with a log on one side, numbers on the other side. That's done. Step 2, use properties of logs to get a single log. Well, notice we have log of something plus log of something. Addition becomes multiplication. So this is log base 3 of x minus 1 times x plus 1 equals 5, which is log base 3. When I multiply these together, it gives me x squared minus 1 is equal to 5. Step 3. Use definition log to rewrite an exponent form. Remember, whatever number is smaller set down here is your b. Whatever follows that is your q, and the other side of the equals is your p. And our exponential form is b to the p is equal to q. So b we said was 3, p is 5, and q is x squared minus 1. And I won't finish that, but you would actually solve that and see what your answers are. Let me show a division. Let's say I had log base 2 of x plus 3 minus log base 2 of x minus 7 equals 3. First step, get everything with log on one side, numbers on the other side. That's done. Step 2, get a single log. Well, we have log of something minus log of something. Subtraction becomes division. So we're going to have log base 2 of x plus 3 over x minus 7 is equal to 3. Step 3, use definition log to rewrite an exponent form. Again, the number smaller follows this is our base, so that's b. What follows that is our q, and then the other side of the equals is our p. So our exponential form is b to the p is equal to q. So b was 2, p is 3, and q would be x plus 3 over x minus 7. And then you'd solve it from there. Let me clear those off. Now remember, if you have natural log ln, base is e. If you just have log and there is no base, it's 10. And actually, I think that's everything. Create exponential and logarithmic models using regression. Let me show that real quick. Let's say I have x and y. And this is 1, 2, 3, 4, 5. This would be 2, 7, 15, 35, and 81. On our calculator, we'll push our stat button, which is right here, and go into edit. So do enter on edit. And if you have any numbers here, then you press your delete over and over to clean those numbers out. There's a very quick way to clean those out, but I'm not going to go over it because we're not going to do as much with this as you would if you're in stats. And then I'm going to type in each number, pressing enter after each one. So I got 1, 2, 3, 4, 5. Right arrow over to L2 and up on my 2, 7, 15, 35, 81. And then you want to exit out after you get those in there. Second mode. Now we want to make sure our diagnostics is on. So we're going to go into our catalog. So we'll do second 0. And then you push this button that looks like X and -1. And that'll take you down to the D's. And what we're looking for is diagnostic on. In the newer TI-84s, this is actually in the mode. Here's diagnostic on. Press enter twice, and that'll turn that on. Now if we do stat, choose calc, then if you down arrow, these are some different regressions we can do. Here's natural log. Here's EXP. Let me choose EXP. And then press enter. Now this says that based upon this, our model, that this is a hat, Y hat. I know it's kind of strange, but that means an estimate. You plug in your A, 0.957, so 0.957, and then you plug in your B, which is 2.463, to the X power. This would be an exponential model. Now, the closer that R is to 1, the better the model is, or -1. The R squared is just positive, so the closer the R squared is equal to 1, the better. If I want to see a logistic model, if I do stat, go to calc, and I'm going to do an up arrow, see if I can find it faster. I want to choose a natural log right here. And then press enter. Then this would become y hat is equal to, and I'll plug my A in, which is -11.217 plus B, is B positive? Yes. Plus 40.957, and then it says natural log of X. And that would be our logistic model. Now look at what R squared is equal to there. R squared is equal to 0.654, 4 decimal or 3 decimal places. And that's not very good. It's not very close to 1, is it? So it's not that great of a model. So our exponential one is a better one. And that's a regression on the calculator. And I'll go ahead and shut off the video now and answer any questions you have.